All right, we're going to be starting chapter 11, and it starts talking about a geometric sequence, which is a little bit different than the patterns that we've done so far. So this is where each difference is different by something that's constantly multiplied. So if I look at this first pattern right here, I know that it's not linear because it goes up by 2, and then 6, and then something even more. So it's not the same. I could continue that and get my second difference, and it won't be quadratic. I can also do the third new pattern, which is 81 divided by 27, and that gives us 3. 27 divided by 9, that gives us 3. 9 divided by 3 gives us 3, and 3 divided by 1 gives us 3. So this is a geometric sequence, and we have a constant multiple of 3. In the next one, we could do the exact same pattern, 0.25 divided by negative 1 divided by 4, 4 divided by negative 16. Every single one of those gives us 1/4. Negative. Then we're going to find the next 3 terms. So we need to figure out what our constant multiple is. So negative 40 divided by 20 is negative 2. 20 divided by negative 10 is negative 2. Negative 10 divided by 5 is negative 2. So again, we're getting this by dividing. So we would multiply to go forward. So our next term would be negative 40 times negative 2, which is 80. Our next term would be 80 times negative 2, which is negative 160. And our third term would be negative 160 times negative 2, which is 320. We're going to do the same exact thing with the next set of numbers. So 288 divided by 384 is 0.75. And 384 divided by 512 is 0.75. So to get the next number, I would multiply by 0.75. So if you use a calculator and you type 288 times 0.75, you get 216. That times 0.75, you could also do 3/4, is 162. And that times 0.75 is 121.5. So this whole page is all geometric sequencing because they all have a constant multiple. And that's what we just did. And I'll move that down. So if you think about this with letters, the first term we're going to write as a sub 1. That little bottom, it's just telling you that it's the first term. And then each time we multiply it by the constant multiple. So for the second term, we multiply it by the constant multiple once. For the third term, we multiply it by the constant multiple twice. For the fourth term, we'd multiply by the constant multiple again, so 3 times. So for the nth term, this is our formula for a geometric sequence. You take the first term times the constant multiple, or the rate, to the n minus 1 times, because the first term you're not multiplying by a number. And again, this is for a sequence. Okay, so we're going to find the 6th term in a sequence that starts with 5. So our a sub 1 is 5. And has a growth factor of 4. 6th term. So we're going to do 5 times 4 to the 5th power. I should put 6 minus 1 so I understand where I'm getting the 5. We can put all that in the calculator just to make sure you're understanding exactly what's going on. Our first term is 5, and then every single time we're multiplying by 4. So our second term would be 20. Our third term would be 80. Our fourth term would be 320. Our fifth term would be 1,280. And our sixth term would be 5,120. So let's just make sure that's what we get. In the calculator, you're going to put 5 times 4 to the fifth, and sure enough, you get 5,120. A little bit easier than generating the whole table. So in number 2, our first term is 2, and then we need to find what our constant ratio is. So if we divide negative 54 divided by 18, we get negative 3. And 18 divided by negative 6 is negative 3. And guess what? Negative 6 over 2 is also negative 3. So our ratio, our constant multiple, is negative 3. So since our geometric sequence is a sub 1 times r to the n minus 1, that's number of terms, we're going to do 2 times negative 3 to the 9 minus 1. So 2 times negative 3 to the 8th. And if you put that in your calculator, you should get a positive number. You need to make sure the parentheses are around the negative and the 8's on the outside so that the negative is also put to the 8. So 2 times negative 3 to the 8th. 1, 3, 1, 2, 2. Okay. If we know we have a geometric sequence and the 10th term is 3584 and the 11th term is 7,168, we can find that constant ratio by dividing. So if you put in your calculator 7168 divided by 3584, you get 2. So how do we know what the first term is? Well, the 10th term is 35,000, or if we think about our formula, a sub n, so that'd be the 10th term, or 11th, or whatever term you want, equals a sub 1 times r to the n minus 1. We know that our 10th term would be the first term times r to the 9th, because 10 minus 1 is 9. So our 10th term is 3584. We still don't know our a sub 1, but we do know our rate is 2 to the 9th. So in the calculator, if you do 2 to the 9th, you get 512. So to solve for a sub 1, you could just divide by 512. 3584 divided by 512 is 7. So our first term is 7. You could check your work and make sure that using that formula, you get that for the 11th term. To write an exponential equation, we have what we just had, which is a sequence, where you have a sub n equals a sub 1 times r to the n minus 1. This is the first term. So that's when x equals 1, or I should say n equals 1. A basic exponential equation is the same thing, except this is starting amount. And starting amount for our equations is when x is 0, and then times the constant multiple to the x power. So since we're using our 0 term, we do not have the minus 1. When we use our first term, we need the minus 1. We'll talk more about that in just a minute. So how much money to deposit initially? That'd be $500. What interest rate is the CD player paying on the deposit? Well, if you have an interest rate of like 18%, your constant multiple would be 1.18. So if you have an interest rate of 37%, you're going to multiply by 1.37. So if you look at this part of it, our interest rate is 3.5%. That's how you get the constant multiple being 1.035, because that as a decimal is 0.035. And then to find the rate, you have to add 1 to the decimal, because 1 keeps everything the same, automatically adds it in, and then you'll increase. So how much money will be in the CD after 6 years? That would be 500 times 1.035 to the 6th. If you put that in your calculator, you're going to get $614.62. There's a 7 there, but we're not going to round up because the bank is not going to round that up for you. So that's going to be your answer. So just a quick recap on this percent stuff. If you had 5% increase, your constant multiple would be 1.05. If you had 1.7 as your constant multiple, you would have a 70% increase. And if you had 0.92 as a constant multiple, that means an 8% decrease, because 1 minus 0.08 is 0.92. 1 is the base number where everything stays the same. All right, so exponents have a constant multiple. So if you see as we go up by 1, in this case, we're constantly multiplying by 2. And again, you can test that by doing 12 divided by 6, that gives you 2. 6 divided by 3, that gives you 2. So this is exponential. We could write our equation. It would be 3, because that's our starting amount, times 2 to the x. That's what this is right here. Over here, as x is going up by 2, it's going up by 2, the y is changing not by the same multiple. So this is not exponential because these numbers are not the same. But this is a little tricky, so if you see that 2, you need to be right alerted. Like if these happen to be 9 as a second, or as a first difference, then the rate would actually be 3, because 3 times 3 is 9, and this is going up by a multiple of 2. So you might just want to put in the missing pieces. It'll be easier to find your rate, or you can understand that. Okay, so basically, we could generate some tables on the graphing calculator. I'm going to actually have you do a little bit of this tomorrow in class. But if the starting amount is positive, so like if you have y equals 3 times 2 to the x, if you look at a graph of that, or at the table, it's going to start at 3. I'm just going to do this on the calculator. So if a is positive, so let's make a 3 times 2 to the x. So if you look at a table of this, we start at 3, and then we're constantly doubling. All right? How do you think this is going to change if a is made to be 0? So 0 times anything is 0. So you think that's going to be exponential? It's going to always be 0. So that's just like a flat line. If you look at a graph of the first one, we're going to start at 3, and then we're going to double each time. The second one is just a flat line at 0, so that's not even going to be seen. Okay, the next one is if A is negative. So let's go ahead and, whoops, oh boy, make this a negative 3. I got to go back up and put my parentheses back in here. Okay, hold on. Okay, so if you look at the graph, whoops, I meant to do the table. Okay, we'll look at the graph first. So if you look at the graph, we start at 3 positive and double for the first one. The second one, again, was 0, which I got rid of. And the next one, we started at negative 3 and doubled that. So that would actually be going down because the negative is doubling. So if you look at the table for that, we're going down, 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 down. So now let's go back to y equals, and let's make the b part of it positive is right here. So that would look just the same. The bigger it is, like let's make this a 5, then the quicker the numbers are going to increase and the steeper it's going to get. See how they get way bigger, way faster? And that's what an exponential does. So if you look at the graph of that. Now if the b is 0, again we're going to get the flat line because 0 times anything makes everything 0. So I'm not going to bother with that one. And then if the b is negative, if we make this, actually I'm just going to go down and do another one. So let's do 3 to the negative 5 times negative 5 to the x. And then let's go ahead and do negative 3 times negative 5 to the x. Now, this is a little, whoops, 2 to the x. Weird to have a negative exponent because if you look at the table, it's going to go positive, then negative, then positive, then negative. So this is good for the sequencing, but to actually write an equation with a negative 5, the graph isn't even going to show because it's going to go positive 3, negative 15, positive 75, negative 375. It's going to go up and down, up and down, up and down, higher and higher and higher. So this is actually not an exponential equation. The b would have to be positive. It is okay in the sequencing, but when we write our exponential equations this year, our b's will always be positive. So if you look at the next 2 slides, we've basically gone over that completely. And the last thing I wanted to explain, if we go back here, is if you have a linear table, so let's say 0 gives you 3, 1 is 5, 2 is 7, 3 is 9, and 4 is 11. Our basic equation, because this is increasing by 2, so this is our m, and this is our b, is y equals 2x plus 3. Now, I can actually write this linear equation with the first term if I want. But if I use my first term as my b, my x needs to become x minus 1. If you distribute this out, 2x minus 2 plus 5, you get the same thing. I could use my second term to write my equation. That means my starting amount would be 7. But I need to have an x minus 2 because I have to get rid of that 4, still getting the same equation. So when we're writing our exponential, we could use any starting amount to get our equation. So if we start at 0 gives 1, and if we're doubling, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. I could write this as starting amount times constant multiple to the x power. I could write this using the first term, and this is kind of what the sequence looks like. So 2, meaning that 2, times constant multiple, but then I would have to have an x minus 1. I could write it like this, 4 times 2 as the constant multiple to the x minus 2. I could write it using my third term as 8 times 2 to the x minus 3. A quick reminder that 2 to the 0 is 1. 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. 2 to the negative 2 is 1 over 2 to the positive 2, which is 1/4. 2 to the negative 3 is 1 over 2 cubed, which is 1/8. 2 to the negative 4 is 1 over 2 to the 4, which is 1/16. So in each of these, if you simplify this equation, this is your base equation, and that's the base of writing exponentials. All right, I hope this makes sense. Have a great evening.